breaking down a high energy compound. So this part here, I mean, all the parts of the wheel, the cycle, are important, but that top part is driving the previous reaction that doesn't want to go. Okay, so acetate comes in and is condensed onto this 4-carbon molecule, OAA. So citrate synthase is often called the condensing enzyme. You may call it that. You're condensing 2 carbons onto something that's 4, and you make this 6-carbon intermediate citric acid. So you and I are familiar with citric acid in fruits, oranges, lemons, that kind of thing. Well, citrate is part of the Krebs cycle. So citrate is then converted into isocitrate, this thing down here. Now, I'm not sure why Leninger decided to throw in this intermediate. It's cute, but we don't have any other intermediates in the entire cycle. What they're trying to show, and we'll elaborate this more on Monday, is that a water molecule is taken off and a different water molecule comes in. Now, waters are often reactants or products in a reaction. There's lots of water, it's not a surprise. What happens here, though, is that there's a cis double bond. So I would like my students to know that in the reaction of citrate going to form isocitrate, there's a cis double bond, and that water is what creates, the absence of the water creates that. And then addition of a different water comes in, because over here, when this compound, succinate, gets made into fumarate, you form a trans double bond. So this cycle has 2 double bonds. The first one is cis, the second one is trans. The geometry matters to these enzymes. They're very stereospecific. So what this enzyme aconitase does is it takes this OH group right here on this carbon, and it just moves it down to this carbon here. So if you look down here, now the OH group is down here. Now, if we come back up to here, you can't make a keto group here. The cell wants to make a keto group, but if you change this OH into a C double bonded O, what's the problem? And I'm not worried about the CO2 part. There's a double bond O here. It'd have 5 bonds to that carbon, which is not allowed. So cells go, well, we want a keto group here to be attacked, but I can't form a keto group right there. So I'm going to move this OH down to this end here and now form a keto group. And we'll show more of this next week. The point is, aconitase moves an OH group down to set up formation of a keto group. Now, here, once you have isocitrate, the next enzyme is a dehydrogenase. And what do dehydrogenases do? They pass electrons onto either NAD or FAD. In this case, one of the reactants, I wish they would show it here, but they show it in a different way. These different dehydrogenases, there are 3 of them, that are forming NADH. This is Leninger's way of saying there's a pool of NADH being made. So let's get back to here. Isocitrate reacts with NAD, and the NAD goes to form NADH, and whenever you write NADH, you always write plus a proton, H+. So isocitrate, though, is also doing something else. It's releasing a CO2. Since 2 carbons enter in the form of acetyl-CoA, 2 carbons have to exit in the form of, as you breathe out CO2. So that CO2 is driving that reaction. It's leaving. So thermodynamically, You see how this arrow here with isocitrate dehydrogenase is a one-way step too. What we've said previously is that every time you have a step that's one way, it's catalyzed by an allosteric enzyme. So this guy up here, the condensing enzyme, citrate synthase, is allosteric. So is this guy here. There is no choice. The free energy drop is huge. It must be controlled. So our first CO2 has come off, and now we form this thing called alpha-ketoglutarate. It's only 5 carbons because you just lost a carbon. You had 6, you lose 1, you've got 5. Alpha-ketoglutarate you may just call alpha-Kg. And now the next dehydrogenase comes along. Again, not shown in this diagram. NAD is another substrate. The electrons from alpha-Kg are going on to NAD to form NADH and what? A proton to balance the reaction. And once again, a CO2 is coming off. So now you've lost the 2 CO2s. You've lost the 2 carbons that entered as acetyl-CoA. But you're making all this NADH, and where's the NADH going to go to? The electron transport chain, which we haven't discussed, but we will tear apart. So all these NADHs are going to go and dock with complex 1 of the electron transport chain. And that electron transport chain is going to create a massive proton gradient, which is going to drive a motor that makes a lot of ATP. So this cycle right now is indirectly making a lot of ATP because it's creating the proton gradient in the form of the electron transport chain. So, down here you see another CoA. You start to see how CoAs are important. Remember, coenzyme A was a substrate in the PDH reaction. CoA here is going to be used to form succinyl-CoA, right here. This is a 4-carbon thioester to CoA. This is a high-energy compound too. So the cells need the chemistry of the sulfur to be in the SH form so that it can react in these reactions that require the formation of a thioester. Succinyl-CoA will then donate a phosphate to most organisms on the planet. It's being donated to GDP, guanosine diphosphate, to make GTP. I would prefer that you emphasize and know that. In a few species on the planet, it's donated to ADP to make ATP. But I would expect you to know that the main thing here is GDP going to GTP. Why, Dr. Hilt, does it make GTP? Well, we've already talked about in our discussion of carbohydrate metabolism, there are some G proteins that need GTP, correct? And the cell also needs GTP for other things. But GTP has just as much energy as ATP, and there is an enzyme that will convert GTP into ATP if suddenly we need more ATP. So the point is, life is making GTP here for most organisms, including you and me, on this planet. All right. This thing that converted alpha-Kg into succinyl-CoA is the alpha-ketoglutarate dehydrogenase complex. This thing, for right now, is virtually identical to the PDH complex that you learned. So what does that mean? The alpha-ketoglutarate complex isn't one enzyme, it's 3. And we'll just call it E1, E2, and E3. It is slightly different in E1 because the first thing that this complex recognizes is alpha-ketoglutarate, not pyruvate. In the PDH complex, remember the first thing that comes into the soccer ball was pyruvate? This complex is a smaller soccer ball, not quite as large. So 10 million molecular weight, it's more like about 6 million molecular weight. But it's got that same organization with the arm waving with the E2s and things, okay? So E2 is a little bit different because E1 is different. But E3 is identical to the E3 in the PDH complex. Life has figured out a way to do something efficiently, and it just tweaks it a little bit. So here the soccer ball is tweaked so that E1 is different. E2, which links E1 to E3, has to be a little bit different because part of what it's contacting is E1, which is different. But the overall arm waving and everything that we discussed is the same thing. Now the next thing to say is that once you've made this GTP and you form this symmetrical molecule succinate, the next enzyme, as far as we currently know, which I'm sure is wrong to some extent, but what we can prove is succinate dehydrogenase is the only enzyme in the entire cycle that's embedded in the inner membrane. So let's imagine that I am succinate dehydrogenase. Part of me, the part that's doing this reaction, is out here facing you guys. You're in the matrix. You're molecules that can diffuse to me, and I can make this conversion of succinate into fumarate. But the substrate that's missing here is FAD, and this part of the slide is wrong in the sense that it kind of indicates that there's a pool of FADH2, because that's what this is indicating over here. No. I have, as part of my structure, FAD. FADs are always tightly bound to whatever protein they're bound to, which has a real impact because you'll never find in a table of redox values one value for FAD, because it always depends on the enzyme that it's tightly bound to. So, to go back to our story here, I succinate dehydrogenase. The part that's changing succinate into fumarate is out here. My active site is facing you guys who are in the matrix. Just your compounds floating in the matrix. If one of you is succinate, you can bind to me. I'll pass your electrons to my bound FAD, and then it goes beautifully into the electron transport chain. Because me as succinate dehydrogenase, I'm only part of something called complex 2. So it's beautifully built that I send my electrons one at a time, because remember FADH2 is a gear shift. It takes 2 electrons, but then it safely passes one at a time.